Good afternoon, everybody. I am very pleased to welcome you back from lunch. Again, to remind, my name is Jonathan Elkind, and I'm with the Center on Global Energy Policy. Our next conversation looks at cutting-edge research and its relation to climate solutions. So we've had different slices of the climate change issue throughout the day. There'll be more later when we get into a policy-oriented discussion, but now we're looking at the interplay between the research space and climate solutions. Let me remind you, please, that you can submit questions for the panel by tweeting us at Columbia U Energy or using the hashtag CGEP Summit 2019. Again, that's hashtag CGEP Summit 2019. Or you can text questions using the text number, not fax number, the text number that is on the small cards on your tables. That is 347-621-7399. Let's jump into our next segment. We are very pleased to have with us Dr. Arun Majumdar and Sir Alex Halliday to talk about this important issue of the interplay between the research community and climate solutions. Dr. Arun Majumdar is the J. Precourt Provostial Chair Professor at Stanford University, a faculty member of the Departments of Mechanical Engineering and Material Science and Engineering, and co-director of the Precourt Institute for Energy. Dr. Majumdar's research focuses on electrochemical and thermochemical redox reactions that are fundamental to a sustainable energy future, multidimensional nanoscale imaging and microscopy, and a new effort to re-engineer the electricity grid using data science, including deep learning techniques. In 2009, Arun was nominated by President Obama and confirmed by the Senate to be the founding director of the Advanced Research Projects Agency for Energy, ARPA-E, where he served until June of 2012. He then served as the acting Undersecretary of Energy, overseeing DOE's applied energy programs, as well as cross-cutting R&D efforts such as Sunshot and the Grid Tech Team. After leaving Washington, Dr. Majumdar was Vice President for Energy at Google, where he created several energy technology initiatives, especially at the intersection of data, computing, and the electricity grid. Arun is a member of the National Academy of Engineering and the American Academy of Arts and Sciences, received a bachelor's in mechanical at IIT Bombay in '85, PhD from University of California, Berkeley. Dr. Alex Halladay is the director of Columbia University's Earth Institute, which he joined about 1 year ago. Before coming to Columbia, Dr. Halladay spent more than a decade at the University of Oxford, during which time he was Dean of Science and Engineering. He has been a pioneer in developing mass spectrometry to measure small isotopic variations in objects as different as meteorites and living organisms, helping to shed light on the birth and the early development of our solar system, the inner workings of the Earth, and the processes that affect Earth's surface environment. His scientific achievements have been recognized through numerous awards, including the Murchison Medal of the Geological Society, the Bowen Award and Hess Medal of the American Geophysical Union, and many others. He's a Fellow of the United Kingdom's Royal Society and a Foreign Associate of the U.S. National Academy of Sciences. So we have, as you will see, two excellent speakers for the topic at hand. I will again remind that you can submit questions by tweeting at Columbia U Energy or using the hashtag CGEP Summit 2019 or texting the number that is shown on the cards on your table. Let's kick off, if I might, with a question relating to science communication. In the United States, debate over climate science has certainly dominated the headlines and has taken up a lot of oxygen in terms of our politics at certain times. despite years of apparent scientific consensus over the main features of our climate system. So I'd be interested to know your views. Why has it been so hard for the research community to have its findings gain traction in the US political world? And what can the academic world do to improve the business of science communication? Do you want to start off, Alex?
Sure. So, well, thank you very much for inviting me. It's wonderful to be here. It's great to be living in New York. It's great to be here at Columbia. And it's wonderful to be part of what the Center for Global Energy Policy is doing. So it's fun just to kick off with that. So I just wanted to say that I think it's very interesting coming here from elsewhere because things are so highly politicized in this country around the issue of climate and energy. And it's not like we don't all want to sort out the problems and we don't understand them, but the fact that it's become so political is quite unusual, certainly coming from Europe. And I think part of the problem we've got is that, America, of course, has the strongest industry in the area of space and aviation. It's got the strongest industry in oil right now, oil production, now having moved into the #1 slot. But it's also, for many years, been the #1 automobile producer as well. So it's now gone down to #2 behind China. But actually, this actually means that there's a huge vested interest here in terms of the US economy, in terms of how do we protect this wonderful way of keeping ourselves and our standards of living high. And you can understand why it might be difficult to swallow information that suggests we've got to change things. And many people have been doing this for many years. I was with Jim Hansen this morning, actually. And, of course, he's been sounding the alarm for many years that we need to think about climate change, but it's been quite a hard one to take. Climate scientists, I think, just to finish off, to some extent haven't helped, but it's not necessarily their fault. The understanding the Earth system and how it's changing and trying to predict it is immensely complicated. And trying to get our head around what's happening is kind of something that we're figuring out as we go along. And so our predictions now are very clear, and our understanding of what happened in the past, what we should be worried about for the future, is much clearer than it was. But even then, understanding how the climate system is really going to change over the next 50 years is something that is going to require a great deal more work in the future. And scientists haven't been great at really communicating the level of uncertainty and how one nonetheless takes decisions even though you're dealing with an uncertain situation.
Please, Arun.
First of all, I also want to thank Jason, you, and the whole team for putting this together. Thanks for inviting me. I'll make 2 points. One is that when we talk about climate change, we often talk about 1.5 degrees, 2 degrees, 2.5 degrees, etc., which is technically accurate. But what matters to the people, those 2 degrees and all, they miss the larger impact because, and so Jim Hansen actually had a wonderful paper about 6-7 years ago, which showed that the average has certainly gone up, but around the average there's a distribution. And the tail of the distribution has a disproportionate effect on people's lives. We should be talking about the tail of the distribution so that people understand. These are the heat waves, the cold waves, the excess rainfall, the flooding, and the impact of all that on livestock, on agriculture. That's what people get affected by. And I think we probably have not discussed that enough. Not that we have not discussed. But if you want to relate the scientific fact to the actual impact on people, to get people to understand that the connecting of the dots need to happen much stronger. So that would be, I would say, the one issue that we could do a little bit better. The other thing is that, yes, we understand many aspects of climate change. We have models that can predict some things. There are certain aspects that we don't understand. And I think we should be, not that we're not being transparent, we should be perhaps more transparent to say that because we don't understand, that does not mean that there's risk not there, right? For example, we don't quite understand what will happen if the permafrost in the Arctic, they start warming up And the carbon that is already stored in there gets digested, and methane gets produced, or CO2 gets produced. That is a tipping point that we don't quite understand. And that doesn't mean that it's going to solve the climate change problem. It can get even more aggravated. So we may be even more conservative in our thinking. And I think we need to highlight some of the risks that can happen if we don't. And that may not be captured in our models, and that's okay. But we should certainly relate that and convey that message.
Well, let me jump in here. You are highlighting a form of uncertainty that goes in the direction of potentially worse, aggravated climate change. It seems to me that many times the political discourse is around suggesting that the uncertainties have a tendency to exaggerate the sense of climate change. I guess your point, if I were to try to paraphrase it, and please keep me honest, is let's remember that uncertainty works in both directions.
Absolutely. I mean, I think there's uncertainty even in some of the most established aspects of science. I mean, we know Newton's laws. If you put Newton's laws in a nonlinear system and you have many body things, we can't predict exactly what's going to happen. We can't predict turbulence properly. That does not mean we don't build our planes to account for turbulence. Okay? That's a nonlinear thing.
So what should the implication of the remaining areas of uncertainty in the scientific realm be for decisions made, not made, today or delayed? What should be the implications for policy of the uncertainties that remain in the climate system?
I would say we really have to, it's all about risks. And what do we account for? And one of the things that happened in Washington when you and I were there was the BP oil crisis, Macondo, Deepwater Horizon. And one of the things that we realized that was happening is that you can't you can't prepare for the best and then hope for the best. Okay, you got to hope for the best, but you got to prepare for the worst. And I think there's a risk involved, that the risk has to be conveyed, and we need to prepare ourselves, whether it's clean energy and infrastructure and all aspects of our economy, that has to prepare for some element of the worst. And I think that's the accounting that we need to do, and we need to convey that.
Yeah, so I think the magnitude of the risk, I totally agree. And I think the magnitude of the risk hasn't really been taken on board, and people are getting more and more worried about it. It's partly the tipping points that were, but at the same time, it's also some aspects of the system that we are building evidence around, which has to do with how things happened in the past. So I'm a geologist, so I've been studying things that the Earth's 4.5 billion years old. If you just go back 1% in the history of the Earth, you're back a mere 50 million years ago. 50 million years ago, there were no ice sheets. Okay, things were 10 degrees or more hotter on the surface of the Earth. There was no Antarctic, there was no Arctic glaciation. It wasn't until about 40 million years ago that we started to build up ice sheets in Antarctica, and things gradually have been cooling over the last 50 million years. And this has been the way the natural world is working, and we have some geological theories as to why that's happening. And so 3 million years ago, we started to get the buildup of ice sheets in the Arctic. And we started to see, we can see what happens in terms of ice ages coming and going. We can do ice cores through the Antarctic ice sheet and see the change in CO2 and temperature over the last 500,000 years. And we can see that, basically it oscillates between 100 and 300 ppm CO2 in the atmosphere, depending on whether you're going through a glacial or interglacial. Glacial, more CO2 goes into the oceans, and conversely during interglacials. Right now we're in an interglacial, and you can see what's happened in terms of this cycle of CO2 and temperature in the last couple of thousand years, where we've had roughly 300 ppm until basically James Watt builds the separate condenser steam engine, which transforms the Industrial Revolution. And we see CO2 starting to rise dramatically at a rate that's faster than ever before, as far as we can tell, in the history of our planet. It's absolutely dramatic. It's forcing major change on the planet. And it's been known for over 100 years what this will do. And Arrhenius and other people who thought about it thought it might be quite nice to live in a warmer world. They already knew that CO2 was going to increase the temperatures. So now in the last century, we've seen things over the last less than a century, we've seen things increase by 1 degree centigrade at the surface of the Earth. There are major implications of this in terms of what will happen to these ice sheets. If you add up the amount of ice we're talking about, if you take the Antarctic and the Arctic, we're talking about over 60 meters of rise in sea level. So that's what's, how long that'll take to come along isn't clear. At the moment, we're going up at about 3 millimeters per year of sea level rise. That doesn't sound much, but 100 years ago, it was 0.5 millimeter per year. So it's accelerating. But people aren't worried about that. If you ask the ice physicists what they're worried about, is that there may be major carving off of ice sheets, which is something they've seen happen in the geological past, and they worry about periods, something more like 4 meters of sea level rise in a century. And they can see this happen coming out of the last ice age. This actually did happen on the Earth for several centuries. We were increasing sea level by 4 meters per 100 years. And that is a devastating effect. We don't know quite how to model it right now. We need the science to really understand what's going to happen in the future.
But again, back to the idea of communication around science. So what would those kinds of changes mean for a New York or a London or many other cities around the globe which are along our seacoasts?
So it's very complicated. So we're not a bathtub where the water just goes up and down. If you take ice off Greenland, you actually lower the sea level. And it's because there's an isostatic rebound of Greenland, and it's also to do with other aspects of the gravitational pull of the ocean towards the subcontinent of Greenland. So there are funny things that happen. We're now getting the data to understand that in detail, and we can see which cities around the world are most vulnerable and which parts of the world are going to have the biggest rises in sea level. And areas like New York City are actually more vulnerable to what's going to be happening in the Antarctic, where the ice sheets are 10 times bigger than we have in the North Pole. And wherever you are pretty much in the equatorial regions, you're basically screwed. So, I mean, it's really, really bad in some of those regions.
It's technical terminology, right?
That's
please.
So one of the things that we have to recognize is that science progresses by debates, by questioning each other. And that is often misconstrued as that we don't agree on anything. We agree, I mean, if this bottle of water is all the issues related thing, we agree almost still here. Almost everyone agrees. We debate on these little issues out here. Is do we really have this coefficient in this model correct or not? Yeah. Or maybe there's a better way to do that. And that is often misconstrued as we don't agree on anything. And that is, then people drive a wedge into this saying that, this is all a hoax. It's not. And I think we need to convey the idea that we agree on pretty much all of this, except for this little thing that is now being debated, but that will be resolved through science. And I think that's a very important aspect of science that maybe the general public may not quite understand.
It's actually slightly, if I can just jump in, it's actually worse than this. The media, to some extent, certainly the BBC, I've got great respect for the BBC, of course, but they for a long time felt that when climate was brought up in the morning program, they basically had to have a climate skeptic alongside a climate scientist so that you could balance these two arguments out. And actually, of course, 99% of the scientific community is totally convinced about climate change, but it left everybody a bit confused. What the heck's going on? Right. And so if the media has that kind of a role of not wanting to sound biased, when actually it's pretty clear what the evidence is now. In fact, it's unambiguous as far as scientists are concerned.
If Alex and I start talking about science, I'm sure we'll find something to debate about.
Right,
That's what we do.
But I mean, this is actually a little bit harder because the very same journalists who are teasing out on the one hand, on the other hand, are in many, many cases, most, not equipped to assess and to evaluate the science themselves. I mean, I'm skipping past undertakings like Climate Central that provides vetted scientific information for the press. But I mean, so is it bad if debate is useful for finding scientific truth? Is it bad to do on the one hand, on the other hand, journalism?
I think there's no question that debate.
I do have an opinion about that, but
Well, I think there's no question. We're in a university, one of the best universities in the world, where you expect there to be debate. Universities should be places where people can argue freely about what they think and what they don't think. So there's nothing wrong with debate and discussion. There is something, I think, wrong with presenting the view that there is some ambiguity about something when actually it really isn't the case. And the scientific consensus is pretty much there. And I think that should apply to policymakers as well. I think they have to be held accountable for how they represent the truth to the public. And that's a very important part that I think we have to.
Good. I'd like to, we've been talking about the more fundamental aspects of the climate system and our understanding of it. But we know from the world of policy that there are some particularly difficult nuts to crack. And I'm thinking here about the hard-to-abate sectors in our economy, the steel and cement and heavy transport and petrochemicals and so forth. What is the role that can be played most effectively by the research community to help think about solutions for those hard-to-abate sectors?
Do you want me to dive in first? Basically, I think it's one of the most exciting areas of science. I mean, one of the great things about energy and climate is it's really fascinating. It's an amazing, interesting issue from the point of view of policy, but it's also very interesting from the point of view of the technical solutions and innovations. And so one of the things that we should be investing a lot of research in right now, including federal funding, is understanding how to take carbon out of the atmosphere and how we can safely store it underground. Everybody should be interested in that. And the federal funding agencies should be pouring money into this as a massive priority. And so getting that message across to government that actually this is really a top priority. And then getting businesses to think about what they can do and the opportunities for them. Because the commercial opportunities are fantastic. And there's so many entrepreneurial ideas in many universities around the world, including Columbia, focusing on carbon capture and use, as well as new technologies around new technologies for energy storage. All of these things are really, really brilliant to be involved in. It's driving a lot of innovation and a lot of creative solutions. And ultimately, when you look back at the history of humankind, there have been massive problems we've faced and challenges, whether it's around food security or water or whatever it is. And eventually, humans actually find a way to get out of it. And that's to some extent where we're headed right now, hopefully.
Okay.
Well, I think if you look at, you're exactly right. I mean, if you look at decarbonizing economy, right now we are very excited about electrification, and rightly so. We're very excited about wind and solar being the cheapest way to produce electricity, and going from coal to natural gas with all the shale revolution. That's all great. That's necessary but not sufficient. Because if you really want to decarbonize, we have to change the transportation sector. We have to look at the electricity, power generation, steel, concrete, food, agriculture. Let's not forget those. So if you think about it, it is almost a remake of our economy in broad sense. Now, that absolutely needs R&D research to come up with new ways, because we cannot always rely on the old ways, because that's what got us here. So we have to come up with new ways, new solutions which are affordable, scalable. Scale is huge. But that's important, but we also need the policy front, which is what I think where you are getting to get this out there. You need to create the markets for it. You need to have the right market structures. Market policy, very important. The regulatory policy. People think that just putting some kind of a price on carbon will solve everything. Well, it'll solve some things. We need some efficiency standards, fuel efficiency standards on the demand side, which are very important to create the markets for many of the efficient technologies. We need to figure out, and I'm so glad that Chairman Chatterjee was talking about going back in history, talking about the Rural Electrification Act of 1936. That transformed the United States. We need to think about infrastructure policy that will get us to the low carbon. It's about developing the technology, but how do you let those technologies provide the services, energy services to American people or the people around the world? You need the infrastructure to deliver that. And so we need to think about it absolutely holistically as to how not only to innovate, but also to deliver the solutions to the people. At the end of the day, that's what it's all about.
So Undersecretary DeBar, before lunch, said, and here I'll paraphrase, I hope I am being faithful to his core point, that policy comes and goes, regulations come and go and have inefficiencies associated with them, but innovation endures. Is it not the case in your two respective views that innovation can get us to the climate solutions that we need? You seem to be hinting, Arun, at using also policy and regulatory tools in addition to the innovation space. Is that, did I understand you correctly?
So it's a question of urgency. You know, we have an urgent situation. If you want to keep the global average temperature rise below 2 degrees, we can emit about 800 billion tons of CO2 more. After that, our emissions have to be zero. And if you're emitting at 40 billion tons a year, we have 20 years or less. So it's an urgency issue. If you really want to accelerate, you can depend only on innovation, which I think we can do. But if you want to accelerate, we need the right policies reinforcing each other to bring these things into the market, into people's lives. And I think that's the acceleration is absolutely critical right now.
I just think, I totally agree, but I think what's interesting is that investors are thinking quite creatively about this already. So they are thinking about new opportunities and areas in terms of which are going to be the transformative technologies, et cetera. And there's some amazing, I've just come back from China meeting some wealthy entrepreneurs and investors, very interested in energy storage in particular. And there are fantastically interesting ideas coming out in that space right now, which could transform our ability to use renewables reliably. And so that's the kind of thing that the big thinking where money is flowing to get behind these new technologies in the broader world.
So I want to latch on to this, kind of the areas that you each see as being particularly exciting, particularly promising. One of the questions from the audience asks, how significant are new hydrogen breakthroughs, including discovery of an aluminum alloy that acts as a catalyst to release hydrogen from water at room temperature with 100% efficiency? Address that if you wish, but my question more is, where are the really exciting frontiers that you see in the research space that have great promise for actually finding those climate solutions?
I think grid-scale storage, as you were pointing out, if you want to do multi-day storage, you need a storage solution that is 1/10 the cost of lithium-ion batteries. We don't have that today. We need R&D to do that. Hydrogen, as you pointed out, is going to be a huge effect. Hugely important. And today, hydrogen is produced from methane, mostly. And if you want to produce hydrogen, carbon-free hydrogen from renewable, we cannot do that at that cost today. It's about 3 times to sometimes 4 times the cost of what you can produce from carbon sources. If you could figure out a way, and this requires research, to bring down the cost of hydrogen, carbon-free hydrogen, because that is the link between the renewable side to the carbon side. Because if you want to do anything to do with turning CO2 into something useful, the utilization part, you need hydrogen. And so carbon-free hydrogen is going to be hugely important. And I can go on, but I think you're getting some time limits out here.
Please.
Well, just basically, I agree. I personally, carbon removal I see as the most exciting thing, negative emissions. And IPCC has basically made it, UN has made it very clear that we actually need to go to negative emissions, whatever pretty much the scenario we go for. There's one other bit of research that is really needed, and it's difficult, and it's messy, and it's complicated. But given that the climate system takes a while to adjust, decades, we're going to carry on seeing temperatures rise and sea level rise and worsening climatic conditions for quite a while to come, no matter what we do. And we have to get people to work on the complicated systems that are going to be evolving across the planet that will involve looking at security, food security, major issues around migration, and manage retreat from certain parts of the earth. And people haven't really started thinking about this as hard as they need to be thinking about it for the future. And the US military is interested in this.
I'll just add one more thing. I think we are often talking about mitigation, but it's likely that we're going to cross 2 degrees, 3.5. That's what we kind of and then adaptation becomes hugely important. The resilience of the system, the ecosystem that we live in, and our lives. I mean, we have to look at adaptation very carefully.
Well, that provides, I think, an excellent bridge to the next segment of our discussion, which is looking at new challenges in energy geopolitics. Jason Bordoff will return in the role of moderator. Ladies and gentlemen, please join me in thanking Dr. Arun Majumdar and Dr. Alex Halladay.